Okay, so section 4.4. That's the next thing. This one is kind of long. Coming back to physics, state properties of an ideal gas. So why are we spending so much time talking about ideal gases? Because, remember, it makes a physicist's life easy. When we talk about non-ideal gases, it's basically engineer's problems or chemist problems. So we only deal with ideal gases, and then when you are doing your engines and stuff, we'll talk about the fact that a lot of times we will deal with situations where there is ideal gas, do the calculation, and then figure out how wrong those calculations were in real life. That's how you do thermodynamics. Good? Okay. So what are state properties? Pressure, volume, and temperature, right? Good. So that means in order to specify the state of a system, we have to define properties. In general, to specify a complete state of a system, if we can define at least two properties. So if I am looking for energy, if I can tell you the TV of the system, or I can tell you the PV of a system, or I can tell you the PT of the system, I will able to completely define for you the state of the entire system. However, under certain conditions. So what are those conditions? So conditions, number one, our processes do not involve chemical reactions. And number two, our processes do not involve changes in phase. So there are a couple of things we're going to do. Number one, I'm going to define for you internal energy. Delta U for ideal gas. Anybody remember the first law? Guys, we should really remember this law. It is going to become essential. The first law. What is delta U? What is Q? What is W? And what is the definition of W? Good, right? Heat into the system is positive or negative? Heat out of the system is negative. Okay, work done on the system is what do we call that work?
That's work that's being done to the system.
On the system is, what do we call it? Compression. Somebody said that. Who said that? Good job. Compression. Heat done by the system is, and it is positive or negative. Good. We have to remember that, right? So heat in, the way I remember it is I remember this equation, and then I say, okay, what will increase the temperature on the left-hand side? If I add heat to the system, will it increase the temperature? If I take heat away, will it increase the temperature? No, it will decrease it, right? So it'll be negative impact. So once I have that, that's the first law. First law is that one. Okay, now I have to come up with some assumptions. Okay, suppose I have a system. Initial volume V1, initial temperature T1, and some final state V2 and T2. Of course, there should be also P1 and P2, but I'm going to try to think if, actually, no, I should do P1 and P2. I'm just going to do P1 and P2. Okay, now remember I said I could take any of these and it would work. So suppose I do the first one. I say that in order for me to define my complete state of the system, I am going to assume, pick a color.
Green.
My assumption is that U is only a function of T and V. And because I have an ideal gas, the particles do not interact, right? Which means U does not depend on distance, which means U also does not depend on volume, right? Volume becomes independent. So then my equation in green reduces down to U is only a function of temperature. Yay, makes our life easier. So then I can study the different processes I had. Okay, leave room for 4. Sylvan, before you yell at me. Leave room for 4. Okay, so then I can study the various processes. Number 1, what process did we have? Constant volume. We could have constant pressure. Bless you. We could have isothermal. And last but not the least, we can have adiabatic. Oh, guys, can you tell me what the specific heat formula was from last week?
Q equals
Q over delta T. Just keep that in mind. Actually, I should not do the subscript V. C was just Q over at delta T. Okay. Okay, step one. Constant volume. What happens? Oh, and I should also write the first law again. So guys, write the first law again. Copy. And then paste here. So these are the two things we're going to need. Oh, I should change the color of it. Red. There we go. Okay, so for a constant volume, what can I say about the first law? So when the volume doesn't change, what happens to one of these terms? So delta V equals 0, right? So the first law reduces down to remember what was W? Oh, I should write W also here. P delta V. Okay. When delta V equals 0, what happens to the first law? Okay. So now from number 2. So this was step 1. This is number 2. And this is number 3. So what can you tell me about Q? From number 2. Have you seen this before in chemistry? And why did I put a subscript V there? Because what kind of a process is this? It's a constant volume. Okay, number 2. Constant pressure. Starting from number 1. Delta U equals Q plus W. I have a constant pressure situation. What will I get? Well, is delta U 0? No. Is delta V 0? No. Pressure is constant. So the only change in this case will be delta U equals constant pressure, heat being added, plus work. Where remember, work was what? P delta V. Okay, number 3. Pick a color.
Magenta.
Here we go. Okay, so for isothermal, delta U equals Q plus W again. What happens in isothermal processes, guys? Delta T doesn't change, isothermal, which means delta U doesn't change, which means this equation is left with, we are left with Q equals minus W. Oh, and then internal energy will become that. Okay, next step. Adiabatic. Anyone remember what adiabatic was? No heat or mass transfer. Well, mass we're not worrying about now. Pick another color. Oh, blue. That is cyan. Okay, so adiabatic process, what will happen? Q is 0. So this reduces down to delta U equal W. Okay, now ready for some math? Always, right?